So good afternoon to everyone. As you should know, today we have the pleasure to have with us Professor Fèlix Llovell from Rovira e Virgili University with a talk entitled Using SAFT-based EoS from Basic Ideas to Practical Applications. Professor Fèlix Llovell is a chemical engineer with a PhD at the Spanish National Research Council in the area of chemical physics. He worked in the Chemical Institute of Sarriá at Ramon University as associate professor for 5 years, and in September of 2020, he started a new position in the Rovira e Virgili University. Dr. Llovell's expertise is on the development of molecular modeling tools for the thermophysical characterization of compounds to improve process sustainability, and his work has been recognized with numerous awards. So I would like to thank Professor Fèlix for accepting our invitation to be here today. And please, when you wish, you can start.
Okay, thank you. Thank you very much, Helena. Muito obrigado. It's really a pleasure to be here and to share this talk with all of you. I'm going to share the screen right now, so I hope that you will see this properly. Okay, so I assume that if you don't say anything, is that you are watching the screen. So as I was saying, it's absolutely a pleasure to be here and an honor to be invited to give this talk to your group that I know quite well. And the idea today is to summarize a little bit some ideas related to SAFT and also to highlight a couple of practical applications. Okay, so first of all, I would like to just you introduced that to me, to all of the people, but I just would like to say that during the last 5 years, I was working at Institut Químic of Sarriá, and now I just joined the Universitat Rovira i Virgili with a Sarah Hunter Fellowship in the Chemical Engineering Department. Okay, I know that you are quite familiar with Rovira i Virgili University, but for those of you who doesn't know, it's located in Tarragona, a city 100 kilometers south of Barcelona. You are more than cordially invited to come when once we go the current pandemic situation. Still with that, I have lots of connections with my previous institution in Barcelona, IQS, and I'm still in the research group of engineering and simulation of environmental processes. Okay, the current research group where I am working with. What is the goal of the research group? The goal is to provide responses to the current society challenges. Okay, and we focus on three main aspects, which are related to climate change, water scarcity, and population growing. Okay. In fact, we apply our work to three main sources, which are water reuse, greenhouse gas treatment, and energy. As you can see here, there are two main pillars. One of them is related to process modeling, which is my area of expertise. And this is the purpose of this talk. And the applications will be focused on greenhouse gas treatment. Before starting with the talking about SAFT and other molecular-based equations, I would like to say that there is a historical competition between experimentalists and modelers, and in fact, this is quite stupid, to be honest. And I know that I shouldn't say that to your group because basically you are a group that combine experiments and modeling, and I am very happy to see that. But sometimes there is this typical competition between modelers and experimentalists, like, oh, well, you are in the lab and you just measure and get a paper, or, oh, okay, you are in front of a computer and you just push the button and get a paper. I would say that scientific knowledge cannot progress without joining efforts, okay? People who does computational modeling needs experimental data if you want to fit and you want to validate your models. But at the same time, experimentalists, they also require models to corroborate their findings, to make their data consistent, and to use this as a tool to screen other conditions that maybe cannot be easily measured in the lab. That said, there are lots of types of modeling, okay? And possibly you have already seen this slide in other presentations, okay? Multiscale approaches, at the end, they can be useful to provide solutions to industrial problems. But depending on the information that you require, you have to go to a very lower scale where the computational time is very intensive, and or to a continuous model where the exactness of your calculations is a bit more rough because you are doing lots of approximations, but you can get quick and quick calculations that can be used for process scaling. In fact, the purpose of this talk is to talk about SAFT and molecular-based equations of state. So we will be moving at a coarse-grained approximation in a mesoscale because we are dealing with molecules, but we are not dealing with atomistic calculations. Sometimes to build our molecular models, we are going down, okay? We're going down to build our model and to understand how the molecules are interacting through molecular dynamic simulations or ab initio calculations. And once we have this information, we apply this to build our process scale. We need good thermodynamics if we want to have good design of our operation units. And now let's go on to SAFT. I know that some of you are very familiar with that, and maybe some others are not. So I will just try to make this make a brief summary. Okay. So SAFT is a very well-known equation of state that is based on what it is known as the Bernheim's thermodynamic perturbation theory. Basically, for those of you who are not familiar, you just have to think that this is a statistical mechanic concept, okay? And that the idea is that you can make a puzzle with your molecule, okay? So basically, you can model your molecule as a sum of contributions, and each one of these contributions provides an energy to the system. The main outcome of SAFT is the addition of a specific contribution to consider hydrogen bonding. Okay, this was done through the Bernheim's thermodynamic theory, and this is the main difference with respect to classical equations of state, such as cubic equations of state, which does not consider this effect. Another difference is the fact that as they are based on statistical mechanics, they build and calculate the energy of a single molecule. So the expression is written in terms of the Helmholtz energy, instead of being written in terms of pressure as classical cubic equations of state. So for this reason, you have a sum of terms, and each one of is giving a contribution to the energy of the system. We have an ideal gas contribution, a monomer term that considers the attractions and repulsions between these spheres, okay? And this can be given by a different intermolecular potential. And then you have two perturbative terms that account for chain connectivity and hydrogen bond formation. The essence of the SAFT equation is the sum of all these terms. And as I was saying, the main difference with respect to classical equations of state is here, okay? You will find in the literature many different names that result confusing. SAFT-BR, SOFT-SAFT, PC-SAFT. You have to consider that the main difference is the intermolecular potential that is selected here in order to consider the interactions between the molecules, okay? In this presentation, I will show results with SOFT-SAFT that uses a Lennard-Jones intermolecular potential, okay? There are some minor differences. PC-SAFT is using a perturbation over the chain, not over the segment, but in general terms, this is the main difference between SAFT versions. And this is something that possibly you will not see in most presentations, which are a little bit the equations that are behind, okay? In the case of the SOFT-SAFT version, which is the one that I am presenting here, that was developed by Felipe Blas and Lourdes Vega already more than 20 years ago, okay, uses a Lennard-Jones term, and the Lennard-Jones term is fitted to Lennard-Jones molecular simulations, and it's basically a correlation that is expressed here. Then you have the chain and the association terms that are a bit more complex and are formally identical in all equations, in all SAFT equations. I'm not going into the detail of the different terms, but just keep in mind that here we have a series of parameters, and these parameters are related to the molecule in the sense that they are related to the physical shape and energy of the molecule. We have from one side M, which is the number of monomers, sigma, which is the monomer diameter, epsilon, which is the dispersive energy. So all these three terms are related to these monomers. How many monomers do I have, and which are the diameter of these monomers, and which is the energy of attraction between these monomers. And then I have two additional parameters which are related to the energy and volume of association of these possible association sites coming from the hydrogen bonding contribution, okay? Here, there is also something that this is interesting to mention, okay? The reference and the chain term could be equivalent to a cubic equation of a state. In a cubic equation of a state, such as Peng-Robinson or Soaverelli-Kwong, you also have the acentric factor, which is accounting for the non-sphericity of a molecule. Here, what we have is a, let's say, more detailed approximation that includes this value, which is called the radial distribution function, okay? At the end, basically, it's the probability that two molecules, two monomers find each other, depending of the distance at which they are. The association term is coming from statistics, okay, from Bernheim's theory. That's why the equation is called statistical associating fluid theory, and it's resolved using this mass balance, momentum balance equation. Once you have your parameters, you need vapor-liquid equilibrium data. Typically, you can also use other sources, but typically vapor-liquid equilibrium data to fit these parameters. Another thing that it is interesting from this type of equations is that you can improve the SAFT by either doing internal improvements on the equation, such as introducing more variance, heteronuclear change, or intramolecular effects, adding new theories to cover areas that are not well described by the system according to the limitations that there are, such as the critical region or the interfacial region or the polarity, on extending the capabilities of the equation just by calculating things that are other properties not typically, not so studied, such as the derivative properties, excess energies, or the formation of aggregates. All these properties are directly given by SAFT, given the nature of the equation. But now I would like to say, there are many questions and many myths that can come from people that does not use SAFT typically, okay? Is SAFT a fully predictive equation? We have heard many presentations saying, oh, SAFT is fantastic, you can predict absolutely everything and so on. Is it true? What are the advantages of SAFT versus cubic equations of a state? Okay, I've mentioned that there is an additional term, but is it really worthy? What does it mean physical meaning? What does it mean transferability of the parameters? Okay, so let's try to give some light on these questions. Okay, so first of all, SAFT is predictive. Well, the response is SAFT equations are not fully predictive. Okay, in most occasions you will need to calculate binary parameters. Okay, if you think about it, binary mixtures, in all binary mixtures, the reference, which is the monomer term, is transformed into a pseudo-pure fluid because there is not an expression for mixtures. Okay, so basically this reference term, you have to convert your two compounds in one. Okay, and for that you use the van der Waals one-fluid theory, and you have to estimate a new segment diameter and a new dispersive energy parameter, okay? So this is given by the Lorentz-Berthelot combining rules, which are calculated with these simple equations. However, here we can see that we have eta and chi. Eta and chi are binary parameters. And to fit these binary parameters, you need at least one isotherm on isobar, okay? Chi is equivalent to the Kij that you can find in cubic equations, okay? Eta is less used and is equivalent to Laj, okay? But you will always find chi unless you have very ideal systems or you are explicitly accounting for all the interactions between these two molecules, okay? If those parameters are given to one, then the calculations are predictions, okay? Well, and the ternaries. Do we have to fit anything for the ternaries? The answer is no. They are predicted from the binary systems and so on. Ternaries, quaternaries, multi-component mixtures, okay? So the question is, yes, we can predict ternaries and multi-component systems, but for binary mixtures which are not ideal or where not all the contributions are well accounted, you need binary parameters, okay? So let's say that SAFT equations can be predictive sometimes or are semi-predictive. Okay, then what is the advantage of using a SAFT equation if they are not fully predictive? Let's put some examples, okay? This is a CO2 molecule, carbon dioxide, okay? And here there are two possible models. A model without considering the polar effect of the quadrupole and another model without this consideration. And this is a model of ethane, a very simple model without hydrogen bonding. Here we can see the BLE performance, vapor-liquid equilibrium, temperature density diagram with A and B. This is CO2, and these are the temperature density diagram. You can see that model A and model B are more or less the same. They provide the same results, very similar, okay? We cannot state that one of them is better than the other one. Okay, so then why using a model that makes our life a bit more complicated? Well, when we move onto the CO2 ethane model, this is a mixture, pressure composition diagram, okay? The symbols are the experimental data, the lines are the SAFT calculations. We can see that here the prediction of the SAFT equation with the model with quadrupole is basically almost perfect, while the prediction of the model without quadrupole is very bad, okay? Can we correct that? Yes, of course we can correct that, modifying the binary parameter, okay? Then these calculations are done with chi equal to 1, so Kaj equal to 0. So these are predictions, and here we can see the effect, the physical meaning of considering one effect in the molecule, okay? And what about Peng-Robinson and Soberelli-Kwong, okay? So these are the parameters that you need to calculate CO2 ethane and obtain the same results as the red line, okay? You have to use these Kaj parameters, which are not 0. I mean, these are not predictive, okay? So this is an example, because here you are missing the same effect that we were missing here, okay? The quadrupole, the polar effect. Another example, cross-association effects between water and 1-propanol. This is water. There is a lot of discussion on the literature, but let's say that water can be modeled with 4 associating sites, 2 hydrogen and the 2 pair of electrons from the oxygens. Okay, so 4 hydrogen bonding possibilities, and propanol can be modeled with 2 sites. There are other people who talks about 3 sites for the OH. Okay, this is the result if you consider those molecules independently. What does it mean? This is a temperature composition diagram, and here you consider that water and propanol do not cross-associate. Okay, they self-associate, but they do not form hydrogen bonds between them, and this is not true. And then the system predicts a false liquid-liquid equilibrium. This is not true. The symbols represent experimental data. If we consider cross-association in our model, if we consider that there is an association, there are hydrogen bonds between them, then you automatically reproduce adequately this vapor-liquid equilibrium. Again, these calculations are done without any KHA, okay? And if you ask Phys to do the calculation with Peng-Robinson and SRK, there will be a message that will say, don't use those models. Why? Because here hydrogen bonds are the key to describe the properties, and these hydrogen bonds are not explicitly considered in those type of equations. So then other models are recommended, such as activity coefficient models or SAFT, etc. This is another example. Now I'm talking about the transferability. What does transferability means? And this is a work that was done some years ago in a collaboration with Professor Coutinho and Mariana Belo Oliveira, who was in your group some years ago. Biodiesels are multi-component mixtures of different fatty acid esters. Okay, so at some point we just wanted to see if we could model biodiesel, okay, in a predictive manner. What does it mean, a predictive manner? Can we describe biodiesel from the individual compounds without doing further adjustments? So for the fatty acid ester, we provided a very simple model without association, because fatty acid esters, when they are alone, they do not self-associate. So we fitted to density, temperature information and vapor pressure temperature data, okay? And we had lots of information for several compounds, but there were some of them of the family that were missing. Okay, one of the advantages of this type of equations is that as far as you have a physical meaning in your parameters, you can provide correlations with the molecular weight if you are treating with this within the same family, of course, just extending, let's say, the chain length, for instance. So we could provide very simple correlations that allow us to calculate other compounds of the family that were not included here because there was no data individually or the data was very scarce. Why this is an advantage? This is an advantage because then we predicted the density of different biodiesels. These are combinations of up to 14 different fatty acid esters. And the information that it is introduced in the system is just the pure component parameters, okay? As far as all compounds are from the same family, there are no binary parameters here. And we can see how the description of the density from 0 to 45 megapascals is quite good. Although not perfect, as you can see, although not perfect, but quite good. Apart from that, we wanted to see what was happening with the interaction with water, which is another of the compounds that will be found, okay? And it was known that there was a key physical interaction between the fatty acid ester and water. As I said before, we had not considered this to be self-associating, but now here there is a hydrogen bond that must be considered if you want to be careful in your model and you want to have reliable results. So here we propose to add the solvation phenomena by adding a specific site that was accounting only for this interaction, okay? Not for the interaction between fatty acids, just the interaction between the fatty acid and water, okay? So we did some approximations. We considered that the energy of association was equal to the energy of water and the volume of association was half of that of water. And we describe water with fatty acids, okay? The lines correspond again to SAFT, and these are, the symbols are the measurements at different temperatures. This is the fraction of water, okay? And you can see this dashed line, which corresponds to the calculations done with another equation of state, which is CPA. In this case, although CPA also the cubic plus association model, here, although CPA also considers association, the simplification behind the cubic part, not accounting for the chain, the radial distribution function that SAFT has, or simplifying it a lot, let's say, it provides not a bad calculation, but a worse slope, while the SAFT equation provides a better slope. Once you have that, it is possible to describe different biodiesels in a similar manner as done before. These are again predictions from the original calculations. And we can see that, although not perfect, we are able to describe with reasonable accuracy the solubility of water in different biodiesel mixtures. Now that I have shown some ideas of the basic ideas of SAFT, I would like to focus on the applications, okay? We can talk about thousands of applications, okay? I am focusing just on 2 applications, but you can apply this type of models to anything you wish, in fact, as far as thermodynamics are involved. As far as I'm working in a group on sustainable processes, we are very concerned about the climate emergency that we are suffering and we will be suffering in the coming years, okay? And here I'm just summarizing several of the regulations that have been approved in terms to reduce the emissions of greenhouse gases, okay? While Montreal Protocol was very successful in phasing out the chlorofluorocarbons that were causing the ozone depletion, we have not been so successful in order to reduce the greenhouse gas emissions that are causing the global warming. Even if we had Kyoto's protocol with the commitment of almost all countries in the world to reduce their emissions, we had the Paris Agreement that we were focusing on reducing the temperature increase to 1.5 degrees. And the Kigali Amendment, which is also an ambitious program to reduce the production and consumption of hydrofluorocarbons, we are still having strong emissions of CO2 and other gases such as fluorinated gases. In fact, we are currently working in a project, in an European project related to the reduction of fluorinated gases by the development of recovery technologies. So, first application that I want to show is if you want to do a study for new absorbents, and in this case, this is a short study done for deep eutectic solvents to evaluate their capacity for CO2 capture. Okay, so I know that this is the group of deep eutectic solvents, so I know that it's a bit risky to talk about this here. You have possibly the person in the world who knows more about this, and but as I was saying, these are fascinating mixtures, and you know that they melt and freeze at when combining a hydrogen bond donor and a hydrogen bond acceptor. They freeze at a lower temperature than that of the ideal liquid mixture, and they have lots of advantages because they can be used as solvents in different types of separations. But of course, we also know that the strength of interactions and between the two components is affecting the physicochemical behavior. So this represents a good challenge for SAFT-type equations of state in order to get a good model of these compounds. So in the last years, there has been, well, I would say people has got crazy with that because there are plenty of new computational studies that have been done and experimental studies. But still, there are not good models for these complex compounds. Here you can see a little bit of the percentages that the different approaches that has been used, okay? But still, there is a lot of room for improvement. Okay, in this case, we started working with this in 2017 approximately, okay? And we started with a very simple model on tetrachylammonium salts with glycols and carboxylic acids, okay? So first of all, we thought that maybe we could use a one-compound approach, although having a one-compound approach had many limitations. Basically, if you change the proportion between the hydrogen bond donor and the hydrogen bond acceptor, you have to change your parameters. So basically, the idea was to keep all parameters constant and have only one composition-dependent parameter, which was the chain length. Then we said, well, it would be more realistic and better to use an individual compound approach for each one of these compounds. Let's see if we can get this information from these properties. This is the results that we obtain, preliminary results that we obtained for one tetrachylammonium salt with 3-ethylene glycol. And we can see this is the description of the temperature density diagram. We can see that the lines match the symbols. And here we can see the molecular parameters of SAFT. We can see that all molecular parameters are constant, excepting the value of M, which changes according to the different proportion that we have in each case of salt. When we move to the two compounds strategy, see this figure, you can see that there are basically no differences in terms of accuracy, and we were able to fit a single set of parameters for each one of these two compounds, which could be used independently of the proportion that we had in the system. Then, according to that, we decided to skip the one compound strategy and focus on the individual compounds model. The individual component model was used to study different hydrogen bond donors and hydrogen bond acceptors. We studied different salts, 2 tetrachylammonium salts with bromide and chloride, and choline chloride, in a collaboration also with, again, Professor Coutinho and Manuel Crespo, that I know that is in your group. And as hydrogen bond acceptors, there were levulinic acid, lactic acid, ethylene glycol, and glycerol. There are others, but these are the ones that I'm showing in this study. We had a more simple model for the tetrachylammonium salts based on 2 associating sites, and this was based on preliminary results found with quantum-based chemical calculations using software such as Cosmo RS and Avogadro for the charge distribution, and a more complex model with 5 associated sites that was done for choline chloride, as this was a molecule that had far more interactions. For the tetralkylammonium salts, we managed to provide reasonable results. And again, here I focus on the transferability. Here you can see that the association parameters in this case for these different tetralkylammonium salts are the same ones. Also, the energy, the dispersive energy could be the same when the anion was kept constant and only the alkyl chain was changed. This makes sense because the alkyl chain is giving more an steric effect than an enthalpic effect. Also the same for the chloride anion. Here you can see that when the salt was remaining equal and the anion was changed, what it was kept constant was the segment diameter. Again, focusing on the difference on the anion, which is more an enthalpic contribution than an entropic contribution. Finally, we can also see that the tetralkylammonium could be, the M and sigma parameters could be related to the molecular weight in an approximate manner. So everything was making certain sense. For the choline chloride, as this is more complex molecule, as I said before, Emmanuel did a very nice work where he used also included solid liquid equilibrium data in order to have more constraints as far as there were more associating sites. It must be said that most of the values of the associating sites were transferred from other molecules, such as the OH from alcohols, for instance. In this case, this is choline chloride with ethylene glycol, and we can see that there is very good agreement for the density pressure and also for the solid line. Emmanuel also tried other systems, such as the chlorine chloride phenol, which was a prediction where no binary parameters were used, and for choline chloride glycerol, where a binary parameter Chi equal to 1.022 was used. The results were very satisfactory. Okay, once we have that, this is something that was done in the past. Now in the present, we have just taken this information and check the CO2 solubility. Okay, so the CO2 solubility is modeled here, such in a ternary mixture manner. Okay, so we have the salt, the glycol or the carboxylic acid, and here we have different CO2 and the CO2. So here we can see the results of the model compared to experimental data. The model is very good in all cases, and we can see that there are really low solubility values. Okay, the solubility values seem to be favored. Okay, in tetralkylammonium salts, they are higher than choline chloride, and the best results are found for TBA and BR and TBACl. Okay, concerning chloride, which is shown here, glycerol improves the solubility respect to ethylene glycol. Okay, in order to do a better comparison, we decided to check the CO2 loading at a constant temperature. Okay, so what I'm just trying to say is that first of all, here we fit our parameters because here we needed we needed to find the binary parameter between CO2 and the salt and CO2 and the carboxylic acid or the glycol. Okay, so then these are not predictions. Okay, these are not predictions. But once we have these, we predict at another temperature, 298, the conditions of the CO2 loading, which is basically the moles of CO2 that the moles of dipeutetic solvent that you requires to absorb a mole of this. And here we can see that TBACl lactic acid 1,2 is the best one, followed by TBA-BR levulinic acid 1,3. Okay, if you do a cut and compare the results at two possible absorption pressures, such as 1,000 kilopascals and 2,500 kilopascals, you can see that again TBA-BR and TBACl are the two best options. Being the two best options does not mean that they are good options. Okay, capturing 1 ton of CO2 would require 37.6 or 15.4 tons of solvent at this at 1,000 kilopascal or 2,500 kilopascals respectively. To give you an idea, MDEA requires around 5 tons. Okay, so these numbers are far worse than classical amines, which are the current technology that is being used for CO2 capture. Okay. However, we also check not only the CO2 absorption capacity, but also the head of regeneration. And here we are checking the enthalpy of desorption. All of this calculated with SAFT, okay? And here in this case, we could see that again, TBACl lactic acid was the lowest, had the lowest enthalpy of desorption, okay? And all the values moved in the range between 12 and 18 kilojoules mole, okay? This is a prediction again from SAFT, and this is 4 times better than MDA, okay? So in other words, we have lower solubilities, but as far as our capacity of absorption is lower, our capacity of desorption is higher, okay? So a balance should be given in this case. Then we also check mass transfer effects by evaluating viscosity and diffusivity. I didn't go through that because I don't have time, but just keep in mind this idea that you can add extra treatments to the additional treatments to the equation of state in order to evaluate other properties. In this case, the free volume theory was used to evaluate viscosity properties using the thermodynamic information taken from SAFT, and the diffusion coefficient was taken from the Wilke-Chang expression, okay? Also with the properties taken from SAFT and the free volume theory. Here we can see that the lowest viscosity corresponds to choline chloride, TABR, and TBABR levulinic acid. And however, our best solvent up to now, TBACl lactic acid, has the highest solubility and the lowest CO2 diffusivity, okay? So now we have a problem because our best solvent is now our worst solvent in terms of mass transfer, okay? So this must be taken into account when you make your choice. To summarize, if we check the working capacity and we check the moles of CO2 per moles of Des, the enthalpy of desorption, we want to be here in this area. We want a high capacity and a low enthalpy of desorption. And here we have TBACl lactic acid and TBABR levulinic acid. However, if we check these balls, the shape of these balls indicate the mass transfer effects. This one is too small and basically means that mass transfer effects are not favorable because the viscosity is very high and the CO2 diffusion coefficient is very low. So in this study, the best choice would be TBABR levulinic acid 1/3. The idea is not to say that these DES are good for CO2 capture because we have seen many disadvantages. The idea is to highlight the capacities that an equation such as SAFT has, more than only checking the solubility of a compound. The second and final application is related to the compatibility of lubricants with refrigerants. Okay, this is something a little bit different, but it is also related to the reduction of greenhouse gas emissions. Now we are talking about fluorinated refrigerants, which have severe global warming potentials, very high, higher than CO2. And in fact, the regulations will phase out some of them, such as, for instance, R134A. There are several replacements that are being studied, and some of them are already being used, such as R450A and R513A, okay, which have lower global warming potentials compared to that one. The problem is that once you use them in a cycle, you have to check what lubricant will be compatible, because if oil of the lubricant comes in contact with the refrigerant, you will have a decrease in the efficiency and it can cause partial miscibility, okay? It is also true that a small leak can be even advantageous because it can act as a corrosion inhibitor, okay? But what it is clear is that you really need to know the compatibility between the lubricant and the refrigerant in order to design a new cycle. Oil must have a proper range of viscosity to effectively lubricate the compressor and provide enough fluidity in the evaporator, but requires also a good compatibility in order to avoid a strong decrease of the efficiency of the refrigerant. So we propose here to use SAFT to evaluate these interactions between the refrigerants, which we're considering using a polar version a polar moment with the dipole moment, which was explicitly considered in the equation, and two families of polyolesters, PEGs and polyethylene glycol dimethyl ethers. Okay, these complex molecules were modeled just as non-associating molecules, as its extremely bulky properties cause a decrease in the dipoles interaction due to the steric effects. So we accounted for this missing interaction using a chi parameter in the dispersive energy. First of all, we describe a new model using this polar version. So here, no association. There are no associations. There are just a polar moment. This is the experimental polar moment, the vacuum experimental polar moment. And this is the fraction of molecules affected by the dipole, which is taken from Avogadro charge distribution calculations, where we approximately check the area that is affected by the polarity. Here we have the description of the pressure, temperature, and temperature density diagrams, which are accurate, as you can see here, with relatively low errors. Okay. We also check, this is also an important check, how the derivative properties work. These are density in one phase and heat capacity at one phase at 3 different temperatures for both of these compounds. As you can see, the predictions in both cases are good. And this is important because this information was not included in the fitting. Okay, so I insist, this is a fitting, this is a prediction. Also, for the PEGs and polyethylene glycol dimethyl ethers, we feed the information of density and vapor pressure, as it can be seen in these figures, and we saw that we have the possibility to correlate the molecular weight of these compounds, to correlate the molecular parameters of these compounds to the molecular weight. Again, we built several correlations, okay, and we could describe PEGs of different chain length and polyethylene glycol dimethyl ethers of different chain lengths. This is the description of the refrigerant. First of all, the vapor-liquid equilibrium of the mixture R134A and R1234YF, which is the ones that form this one. And this is the temperature density diagram of the mixture at the correct composition, at the composition that they form this refrigerant. Once we had that, we proceeded to describe the solubility of the different refrigerants in these specs. And here we found out several interesting features. First, when you decrease, the solubility increases. And secondly, when you increase the chain length of the PEG, immiscibility gap, and they become stronger when you reach PEG 6. Okay, so this is important because this can strongly affect the performance of our system. However, for R134A with PEG 5, which is the only one where information is available, we did not find any miscibility gap. When we are trying the other lubricants, okay, no miscibility gap was found, no immiscibility was found, okay? So this is interesting, okay, because in one case we have a miscibility gap, there are no miscibility gap. In all cases, we use a binary parameter very close to 115. Once we had that, we check the 3 more promising refrigerants, which were, and because we had information for both systems for these 3 refrigerants. So we compared these 3. We predicted the Henry constants based on the previous information on our model, okay? And we saw that lower Henry constants means more solubility, so higher Henry constants are low solubility. This means that the best option for this 1, 2, 3, 4 was PEG 9, and then PEG 5, and finally triethylene glycol dimethyl ether. For R134, it was just the contrary. So what to do? Here we use information not only on the solubility, which should be, there is a tie here, but also on the viscosity. I'm not showing the results because it would take too long, but the viscosity is reduced from 50% from PEC9 to PEC5. Okay, so in this regard, we chose PEC5 over PEC9. There is another important reason. PEC5 has a smaller miscibility gap than PEC9. For those two reasons, we chose PEC5 as a lubricant for our calculations. Here we refine the previous calculations that we had, obtaining a lower critical solution temperature of 331.9. These are predictions, again, based on our previous model. And what we know now is that if we want to avoid any cycle, it is recommended to work below this temperature in order to be sure that we do not have any miscibility gap, any miscibility here. Remember that when there is a leak of lubricant, we will be in that area, okay? Because we will have a lot of refrigerant and a little bit of lubricant, so we will be close to that area. This is the ternary mixture prediction. Again, this is a calculation done based on previous results at different pressures. And this is the operating line, okay? This line, the dotted line, is the dotted line where we can find the composition of R11513A, okay? And here we can see, depending on the pressure we want to work, where there is the limit between the liquid and the vapor phase. These calculations have been done at temperatures lower than that one of the miscibility gap in order to ensure only vapor-liquid equilibrium. Finally, to conclude, we have built a very simple refrigeration cycle, okay, with this is the classical one where you have the compressor, then you have the condenser, the valve, and the evaporator, okay, and we have fixed the different conditions in order to calculate the coefficient of performance, which basically is the amount of heat that you are removing from the system, from the air conditioning or whatever, respect to the total work that you require in your system, given by the compressor, okay? So these are classical thermodynamic calculations where all the enthalpies and thermodynamic conditions are calculated using SAFT, okay? So these are predictions done from our previous model, and we can manage to calculate the coefficient of performance, and we can see how a leak of PEC5 affects the coefficient of performance of our system. We can see that a 10% leak, from a 10% to a 20% leak, the decrease is around 12% on the coefficient of performance, okay? So we're also including here some results for another lubricant, which is triethylene glycol dimethyl ether, which we skipped, okay? And you can see how the coefficient of performance is far lower compared to PEC. So basically, as I was saying, the goal was to guarantee a minimum ratio of lubricant. Let's say that a small leak is good to provide anti-corrosion properties, but then we have not to exceed 10%, because when we move from 10 to 20%, the decrease is around 12%. Of course, this information depends on the temperature of the evaporator, okay? So you have to, this depends on the conditions where your vapor, your refrigerant cycle will work, okay? Let's say that I was indicating here, in fact, we will be working typically in this area, okay? Moving from temperatures from 250 to 280, okay? And in this case, it is clear that a better performance is obtained for lubricant PEC5 as a consequence of the higher solubility of R513A. To conclude, I would like to say that SAFT is nothing magic. It's just an equation of a state which has also limitations, but has several advantages. The idea is that we are based in physical concepts and have coarse-grained methods that have limitations, but can give more information than classical equations of a state when there are interactions that are not specifically considered for those classical equations of a state. I have shown two examples where we have seen that CO2, the eutectic solvents can be modeled with soft SAFT in an approximate manner and can be used to describe the solubility and other properties related to CO2 capture, and also how different molecules such as lubricants and refrigerants can also be modeled in order to find a solution to a practical industrial problem. There is a lot to improve and many open questions because multi-component mixtures are, the information on multi-component mixtures is scarce still. Much work done on multi-component mixtures. The use of the use of SAFT to biological molecules such as proteins or amino acids, I would say limited and difficult. And there are still several numerical pitfalls in the equation that must be also taken into account when dealing with multi-component mixtures. As I say always, I think that the key is to have the right degree of complexity according to the problem at the exactness that you require. I would like to thank you, all of you, and also some special thanks to some of my collaborators. Some of you, some of them are very familiar to you, I guess, and also to funding received from the CAT4Gas project and the Spanish Ministry of Science and Innovation. Thank you very much for your attention.
Felix, thank you very much for this very interesting presentation. I don't know if someone would like to make some questions.
I would like, and it's very quickly, and I apologize for being the first, but I have another meeting at 3 o'clock, so it's better that I ask the questions and move forward. Felix, I was very surprised to realize that you are back to Rovira Virgili. I'm sorry I hadn't followed your movements in the last time, so I didn't know that you were back to Tarragona. I'm really glad to see you back there. Well, you showed at the end of your presentation the things that you are doing right now with lubricant and so on, but what is in your mind, the projects, the ideas, the systems that you will be dealing with in the near future, I mean in the next couple of years, so that we know that you are doing that, and if we are doing something related, we can interact?
Well, to be honest, well, thank you very much. Yeah, it's a recent movement. And concerning your question, Joao, I would like to keep working a little bit more on deep eutectic solvents, but only for CO2 capture or gas applications, but also for other systems such as olefin separations, and particularly I would like to do a little bit with biomass treatment. I have some ideas behind this, and I've seen several experimental works where the capabilities of this type of solvents seem to be very, very promising. I'm also focusing a little bit on fluorinated gases and in general, as far as I have a couple of projects related to that. And let's say that CO2 is so much studied right now. I see a little bit of possibilities there. Concerning developments, the idea is to join a little bit thermodynamics to process scale. So move a little bit and combine developments on SAFT, group contribution, electrolytes, and so on, towards energy optimization and life cycle analysis.
Okay, glad to know. Wish you the best in this new position of yours. I'm sure that you are happy for being there again.
Thank you very much. It's yeah, I'm happy. It's not the best moment to change institution, but it's going well. It's going well.
Yeah. Okay. Thank you. Bye.
Thank you, Joao.
Anyone else? Hello. No one wants to do questions? We have a very shy audience. It seems.
They got bored. They got bored.
No, I don't think so. And I hope your presentation has reached some of our youngest students, because I feel that some of us that works more in the lab has and see this modeling more applied to very fundamental chemistry and so on doesn't have this idea that we can go further by using this, as you show in these final examples. I think this is the most important message of your presentation. I think this is the most important here. Yes.
Yeah, indeed. The idea is my purpose on this talk was to say that I don't want to come here and to present. I know that I have presented many figures, I know. But the idea is not to say, well, here you have one system, and here you have another system, and here you have another system. The purpose is to say, here I have an objective, and I'm using this tool. I have previously shown to you why this tool is useful with, let's say, simple examples, particular examples. And now I'm applying this tool in order to solve a problem that is required by the industry. And I'm moving a little bit forward from, let's say, the classical solubility calculation, just to see, well, listen, you have basically an equation, and this equation can calculate enthalpies, can calculate entropies, and if you add the right information, you can provide the responses as in the same manner that a process simulator is giving you responses, because there is also a thermodynamic model behind it. Okay, so let's try to push this forward.
Yeah. Okay, someone wants to do final question? I don't think so. Felix, the meeting is already very long, more than 1 hour. I would like to finish and thank you very much for accepting this invitation. I know this is a hard time for you, a lot of work to do, but I hope everything goes well. And thank you very much.
Okay, thank you very much for the invitation. It was a pleasure to be virtually with you, and I hope to visit you in the future whenever it is possible. Thank you.
Thank you, Felix.
Thank you so much, Professor.
Thank you very much. Thank you, Mariam. Muito obrigado.
Obrigado.